Hello students, let us start with note, or we can say that note. First one is mod z square is equals to, we know that mod z is nothing but root of x square plus y square. X is what? Real part of z, and y is real imaginary part of z. Okay, so mod of z square is nothing but real part of z bracket square plus imaginary parts of z bracket square. Okay. Second one, real part of z is always less than or equal to modulus of real part of z, which is less than or equal to mod z. And similarly for imaginary part of z is always less than or equal to modulus of imaginary part of z, which is less than or equal to mod z. Third is mod z1 plus z2 is less than or equal to mod z1 plus mod z2. This is a triangle inequality. Fourth, mod z1 plus z2 is always greater than or equal to mod of mod z1 minus mod z2 mod complete. Okay. Fifth one is mod of z1 plus or minus z2 is less than or equal to mod of z1 plus mod z2. Okay. Sixth, mod of z1 plus or minus z2 is greater than or equal to mod of mod z1 minus mod z2. Combined inequalities 5 and 6, if we combine inequalities 5 and 6, we will get modulus of mod z1 minus mod z2 is less than or equal to mod of z1 plus or minus z2, which is less than or equal to mod z1 plus mod z2. Okay. Let us take one example. If point z lies on the unit circle mod z is equals to 1 about the origin, it follows from inequalities 5 and 6 that mod z minus z2 is less than or equal to mod of z plus mod of 2. Mod of 2 is 2. Here mod z is 1, so this is equals to 1 plus 2 is equals to 3. Mod z minus 2 is greater than or equal to mod z minus 2. This is equals to 1 minus mod z is equals to 1, but this is modulus. Okay, so 1 minus 2 is minus 1, but mod of minus 1 is 1. In next line, write down generalized triangle inequality. Mod z1 plus z2 plus and so on plus Zn is less than or equal to mod Z1 plus and so on up to mod Zn. N is greater than or equal to 2, 3 and so on. Okay. Let us take next topic, complex conjugates. Complex conjugates. Complex conjugate. The complex conjugate or simply the conjugate of a complex number z is equals to x plus iy is defined as the complex number x minus iy, and it is denoted by z bar. This is complex conjugate of complex number z is equals to x plus iy. That is z bar is equals to x minus iy. Complex conjugate of this z is x minus iy. The number z bar is represented by the point order pair x comma minus y, which is the reflection in the real axis of the point order pair xy representing z. Next line, conjugate of z is equals to z. Modulus of conjugate of z is equals to mod z. This is true for all z. Okay. This is true for all z. Next line, write down, if z1 is equals to x1 plus iy1 and z2 is equals to x2 plus iy2, then z1 plus z2 bar is equals to x1 plus x2 minus I into y1 plus y2, which is equals to x1 plus x2 minus iy1 minus iy2. This is x1 minus iy1 plus x2 minus iy2. This is nothing but z1 bar plus z2 bar. So this is first. Similarly, we can prove, actually no need of proof, but z1 minus z2 bar is equals to, just keep in mind that z1 bar minus z2 bar. Third one is z1 into z2 bar is equals to z1 bar into z2 bar. Fourth one is z1 upon z2 bar is equals to z1 bar upon z2 bar. But when this happen, z2 bar or z2 is not equals to 0. Okay. Fifth one is real part of z is always z plus z bar upon 2 and imaginary part of z is equals to z minus z bar upon 2i. Okay. 6 is z into z bar is equals to mod z square. 7 mod z1 into z2 is equals to mod z1 into mod z2. 8 modulus of z1 upon z2 is equals to modulus of z1 upon modulus of z2 and z2 is not equals to 0. 9 modulus of z1 into z2 square is equals to z1 into z2 into z1 into z2. This is nothing but z1 into z2 into z1 bar into z2 bar, which is equals to z1 into z1 bar z2 into z2 bar. This is nothing but modulus of z1 square into modulus of z2 square. So, or we can write this mod z1 into mod z2 bracket square. Okay. So mod z1 into z2 square is equals to modulus of z1 into modulus of z2 bracket square. Okay. Let us take one example. If z is a point, inside the circle, centered at the origin, with radius 2, so that modulus of z is strictly less than 2, it follows from the generalized triangle inequality that modulus of z cube plus 3z square minus 2z plus 1 is less than or equal to mod z cube plus 3 into mod z square plus 2 into mod z plus 1. This is strictly less than, here mod z is less than 2, that's why 2 cube plus 3 into 2 square plus 2 into 2 plus 1. This is nothing but 25. Okay. Let us take next example. Use properties of conjugates and moduli to show that first is z bar plus 3i bar is equals to z minus 3i. Here LHS is equals to z bar plus 3i bar, which is equals to use properties of conjugates and moduli. So this can be written as z double bar minus 3i. 3i bar is minus 3i, which is, we know that this is, z minus 3i, because z double bar is equals to z, which is equals to RH. Hence, we have proved which we want to prove. But here we can give a reason. Z1 plus Z2 bar is equals to Z1 bar plus Z2 bar. Okay. Similarly, take homework. IZ bar is equals to minus I into Z bar. C 2 plus I bracket square bar is equals to 3 minus 4i. And last is D modulus of 2z bar plus 5 into root of 2 minus I is equals to root of 3 2z plus modulus of 2z plus 5. Okay. Let us take next topic, exponential form. Up to this we have seen rectangular form of complex number. In rectangular form, complex number is of the form x plus iy. Now we will see exponential form of complex number. Exponential form. Okay. Let r and theta be polar coordinates. R and theta be polar coordinates of the point order pair xy that corresponds to a non-zero complex number z is equals to x plus iy. Since x is equals to r cos theta and y is equals to r sin theta, these are the polar coordinates. Z can be written in polar form. As z is equals to r into cos theta plus I sin theta. Okay. Z can be written in polar form is z is equals to r into cos theta plus I into sin theta. Note, if z is equals to 0, the coordinate theta is undefined. If we take z is equals to 0, the coordinate theta is undefined, and so it is understood that z is not equals to 0 whenever polar coordinates are used. In complex analysis, the real number r is not allowed to be negative and is the length of the radius vector for z. that is R is equals to modulus of Z. Okay. In complex analysis, the real number R is not allowed to be negative and is the length of the radius vector for Z, that is R is equals to modulus of Z, that is R is equals to modulus of Z. The real number theta represents the angle measured in radians that Z makes with the positive real axis when Z is interpreted as radius vector. The real number theta represents the angle measured in radians that makes with the positive real axis when Z interpreted as a radius vector. Okay. Each value of theta is called argument of Z. Each value of theta is called argument of Z. Okay. The set of all such values is denoted by argument of Z. Okay. The principle of value of Z, the principal value of argument Z denoted by argument of Z is that unique value and it is denoted by this notation such that minus pi is strictly less than theta, which is principal value, which is less than or equal to pi. So argument of Z is equals to argument of Z plus 2n pi, n runs from 0 plus or minus 1 plus or minus 2 and so on. When this is small a, this is argument of Z, means it is the set of all argument of Z, and this here is capital A. This is principal value of argument of Z. For better understand, we will see more examples in next video. When z is negative, when z is negative real number, when z is negative real number, argument of z has value pi, not minus pi. When your z is a negative real number, at that time argument of z has a value pi, not minus pi. Keep in mind this. Okay, we will stop here. Before that, we will discuss write down the symbol e raised to I theta or exponential of I theta is defined by means of Euler's formula as e raised to I theta is equals to cos theta plus I sin theta. Theta measured in radians. So polar form is z is equals to r into cos theta plus I sin theta. In exponential form is z is equals to r into e raised to I theta. Okay, this is the exponential form of a complex number. Okay, we will stop here. Thank you.